Hello, my name is Ashton Woods. I'm a geologist with the United States Geological Survey at the Earthquake Science Center in Menlo Park, California. I am very pleased that I will be lecturing to you today on hazard mitigation techniques for Indonesia. Please give me a moment to share my screen and we will move forward with the lecture then. Thank you. Lecture 21, Hazard Mitigation Techniques. Hazard mitigation. To understand what hazard mitigation is, one must first understand the difference between natural hazards and natural disasters. Hazards do not present an immediate harm, yet are ever present in the environment. Natural hazards are capable of evolving into natural disasters. However, a natural disaster cannot occur unless there's an at-risk population within the area affected by a natural hazard event. To understand how to design hazard mitigation techniques, one must first understand and evaluate risk. Risk accounts for any given population that is to be affected during a disaster or natural hazard event. Risk is determined by resiliency score and community knowledge. Community knowledge is key, and we are able to understand community knowledge through several techniques. One such is community awareness surveys. Community awareness surveys involve the public through critical thinking workshops. They help us to build an understanding of what natural hazards exist in the immediate area and how these hazards can become disasters. It allows for investigation into whether a community knows how to properly evacuate or defend their home during disaster events. Another way we assess community knowledge is through community needs assessments. Community needs assessments are normally done on a government to public sector level. This tool addresses the surrounding community to understand if it is up to code, has pre-existing evacuation zones, or ease of access to hospitals during emergency situations. CNAs also help to determine budget and how to implement mitigation tactics against potential disasters that will occur in the future based off of existing hazard data. CNAs delve deep into understanding vulnerability. Vulnerability is determined through vulnerable populations. Vulnerable populations are at-risk populations that are capable of being affected during disaster and natural hazard event. In this chart, we will look at how funding is determined based off of vulnerability. On the top left, we have an urban high-income and insured population normally found in cities. The vulnerability is lower, but they have significantly more funding than, say, the top right example. Suburban areas are considered more vulnerable because the population exists on a minimum wage and are often surrounded by infrastructure that is either uninsured or outdated. The population most at risk on the chart is indigenous neighborhoods, where their vulnerability is significantly high, but they have little funding following a disaster. This is largely due to lack of communication and lack of investigation within indigenous areas. In order to reduce vulnerability and to decrease damage cost within a given demographic, site investigations are crucial. Site investigations are performed through land surveys and require inspection of a vulnerable environment to determine if a hazard will present complications after environmental changes occur, or if there's a hazard that is developed due to anthropogenic activities such as city planning. An example of an emerging hazard would be draining of an aquifer allowing for sinkholes to form as a result of change in the density under the surface. It could also be something as simple as the installation of man-made river channels that presented an increased potential for flooding damage within the area that didn't exist prior to implementation. My apologies. Site investigations are very important to help both the community and local government to understand how hazards and disasters will play out in the future following environmental factors such as heavy rainfall, droughts, or seismic activity. Supplemental information to site investigations are natural archives. Natural archives are useful as these records hold historical data on disaster events. Examples include personal journals or old shipping logs. On a grander scale, natural archives can be museum features. The image you see in this slide is the Nojima Fault, responsible for the 6.9 magnitude Great Hanshin earthquake that devastated the Hyogo Prefecture in Japan. The city of Kobe decided to build around the area of the Nojima Fault that was exposed following the earthquake as a way of bringing public awareness and knowledge to how earthquakes occur and why it's important to understand faults. This is a wonderful example of a natural archive. Let's now discuss early warning systems as a method to decrease vulnerability. Early warning systems are extremely crucial for providing information on potential disasters. Their disadvantage, however, is that they are detrimental in the existence of international collaboration. Lack of communication between international communities can mean data inaccuracies during disaster events. The greater the disaster, the more international collaboration needs to be done to relay real-time and accurate data. It is very crucial that collaboration is involved during the hazard mitigation process. Localized emergency warning systems also rely on communication. These EWCs are often well managed and utilize both remote sensing and geophysical sensors. These sensors pick up data on slight changes in the environment and present this data through geospatial satellites. These satellites send this data to observational facilities, where investigators will determine whether or not emergency managers should be alerted to a natural hazard event becoming a potential disaster. These observational facilities translate this information through communication satellites, which can be accessed by emergency management centers. Emergency managers are then responsible for activating evacuation protocols. How does remote sensing data help us to understand natural hazards? Remote sensing is one aspect of geographic information systems. RS and GIS use satellite imagery to catalog changes on or beneath the Earth's surface. These methods are used for disaster and hazard mapping. GRACE, MODIS, and Pleiades are commonly used satellites for disaster mapping. GRACE is Gravity Recovery and Climate Experiment. MODIS is the Moderate Resolution Image Spectral Radiometer, and Pleiades is an Earth Surface Imagery satellite that uses ortho-rectified color. As technology advances with satellites, we are able to use satellite imagery along with integrative software that can be utilized through mobile application. Here's an example of a disaster emergency response satellite image of Sugihara in the Banten province on the island of Java. The top image is dated August 2019, showing Sugihara. The bottom image is January 2020, showing significant riverine flooding following heavy rainfalls that impacted Jakarta at the beginning of the year. The August 2019 image of Sugihara shows the agricultural layout along with the demographic of the area. Very rural, tight-knit community. The January 2020 image has a legend on the left that I will explain. The blue stars are buildings that were affected. The data is incomplete as it only shows affected buildings that were investigated. There are several places that had significant damage that were not investigated, and so they are not labeled on this map. The yellow circle shows the bridge was cut off, so there was less access to hospital and emergency response teams. From the land survey data available, the image also reveals that at least one building was completely destroyed during this flooding event, designated by the red triangle on the map. It's great to have this information, but having this information alone does not help us to mitigate against future disasters, like potential flooding events in Sugihara. So what can we do? In the United States, we work with the Federal Emergency Management Agency to draw disaster maps. Here's an example of a flood map, initially used to determine types of flood insurance that would be needed for each area. This map is useful as a hazard mitigation tool, as it allows for emergency planners to understand where flooding may occur and at what frequency of occurrence, so that aid can be provided to high-risk areas without compromising the available budget. This particular map is Broward County, Florida, in the United States. Here's a close-up of the area showing neighborhoods, man-made lakes, rivers, channels, and ravines. The next image is an outline of each residential zone at risk of flood damage. The blue and orange zones are labeled as zones A through V, as in victory, as these areas are at significantly higher threat to immediate flood damage. Understanding what these zones are help us to determine during heavy rainfall which areas need to be evacuated first, and which areas would simply need to fortify with preventative measures such as sandbag barricades. The legend for the map is on the left for those of you who are curious to understand the map further. There's a few green labeled areas on this map. These areas are marked as undetermined flood risk as they have not been previously investigated. This feature on the flood map helps emergency planners to understand that the maps require consistent updates and need for a periodic site investigation. Missing information may potentially lead to increased risk and vulnerability To properly mitigate for future events, updates to maps are necessary. Now, it is of great importance to mention that communication is key. Hazard mitigation cannot be successful without collaboration, and collaboration needs to happen between government, private, and public sectors that are willing to involve at-risk communities in mitigation projects. I was inspired to include this video of a mitigation initiative that is taking place in Jakarta with the help of the USAID. The individuals within this community have found a way to bring more awareness and communication about disasters to public attention. So let's play the
There are lack of real-time information during disaster, which is very critical. It can save more lives if we can get that information available in real time. We can collect this critical information by crowdsourcing from social media because Jakarta itself is the highest population of social media in the world. People are willing to share that critical information in real time through their social media. We use that existing information and redesign that and visualize that in real time to complete the information that we gather from the government. The more open we design that, the more lives we can save.
truly inspiring. So let's discuss global initiatives now. Global initiatives. They're crucial for hazard mitigation as global tactics for combating against disasters take mitigation techniques from various international entities. Open source access to mitigation tactics allow for more vulnerable countries to implement strategies that have yet to be utilized within their national borders. Current global initiatives that are in place that I'd like to mention here are the Sendai Framework, the Sustainable Developmental Goals, and the Paris Climate Agreement. The Sendai Framework is purely focused on disaster relief and disaster response. Their goals are substantially reduce global disaster mortality, to reduce number of affected people per disaster event, to reduce the direct economic loss of global GDP, and to reduce disaster damage to infrastructure, while substantially increasing the number of countries with disaster risk reduction strategies, the enhancement of international cooperation to developing countries, and to increase availability and access to multi-hazard early warning systems and disaster risk reduction assessments. One of those strategies provided through the Sendai Framework in collaboration with the United Nations Office for Disaster Risk Reduction involves the use of an online video game platform that allows for real-life scenarios of specific disasters. Video games for hazard mitigation allow for individuals, students, parents, and children to observe different mitigation efforts during disaster scenarios. This particular game, Stop Disaster, allows the player to act as an emergency manager during a chosen scenario and can vary in level of difficulty. It uses real-life data and mitigation solutions that the player can access when determining how best to implement mitigation tactics. After the scenario plays through, a mission report is provided that reveals how many buildings were destroyed, how much of the population was able to remain safe during the disaster event, the cost of damages following the event, and the success of evacuation zones based on the player choices for improving vulnerable areas. In this particular scenario, we see that the school was destroyed. That's an entire evacuation zone that has been lost because it was not properly fortified compared to the hospital during the scenario. This game provides scenarios for tsunamis, hurricanes, wildfire, earthquakes, and floods, as mentioned in the top bar here. On to the Sustainable Developmental Goals of 2030. SDGs are part of the Paris Climate Agreement and are enforced by the United Nations. They're also implemented into the Sendai Framework. 6 different Sustainable Developmental Goals focus primarily on disaster reduction and disaster mitigation and are the following: the Clean Water and Sanitation Goal, the Industry Innovation and Infrastructure Goal, Climate Action Goal, the Affordable and Clean Energy Goal, Sustainable Cities and Communities Goal, and the Life on Land Goal. These goals go into the pros and cons of short-term and long-term solutions. So let's talk about some of them. The short-term solutions for disaster mitigation include dams, levees, seawalls, and building codes. The reason why these are short-term are because the criteria or science behind these solutions cannot perform a fit-for-all function, or simply put, they don't work for every environment on a global scale. Now I want to go into this video, but before I do, I want to also mention an example to better explain why these are short-term solutions. A levee in one area may fail, while another levee 5 miles away may succeed. The reason for contrasting results relies on soil complexities and subsurface variations. Now let's go into the video that I'm about to play, which will feature how changes in soil permeability can cause sudden dam failure.
Flow-through soil follows Darcy's law, which is simple to understand but difficult to calculate in 2 dimensions. Before computer models, engineers used an analytical tool called a flow net to estimate the behavior of seepage. Now, software can do the work more quickly and accurately. Darcy's law essentially says that the rate of seepage depends on the length of the flow path and the difference in pressure across it. The combination of these 2 factors is called the hydraulic gradient. If the difference in pressure is small, like in this example, the seepage will be slow. The bigger the difference in pressure, the greater the seepage flow rate will be. But if you increase the difference by too much, eventually some strange things start to happen. So what's happening here? I've talked about shear strength of soil in a previous video, so check that out if you want more details, but here's the gist. Soil is a granular material that has one main way of holding itself together: friction. Gravity pushes the soil particles together, creating friction, which gives the soil strength. Seepage is the enemy of friction. Water gets in between the particles, pushing them away from each other, reducing the friction and thus reducing the strength. This is important because shear strength is really the only thing that separates a solid from a fluid. In fact, when the water pressure within soil gets so high that it eliminates the shear strength altogether, we call it liquefaction, also known as the quick condition. The soil is literally behaving like a liquid. It's quicksand. You can see why seepage is bad for dams and levees. Engineers generally try to avoid building civil structures out of liquids, and soil liquefaction can be the starting point of a specific type of erosion called piping. As soil is carried away from the dam's foundation, the seepage path gets shorter. Remember that seepage depends on the hydraulic gradient, which is a function of the length of the seepage path and the difference in pressure. If the pressures stay the same, but the path gets shorter, the gradient goes up, creating more seepage. This is a dangerous positive feedback loop. The erosion shortens the seepage path, while the increasing seepage creates more erosion. Eventually, the erosion pipe reaches the reservoir, leading to catastrophic failure of the dam's foundation. This isn't just speculation, piping is the #1 cause of failure for earthen levees and dams. So how do engineers deal with seepage? One common way is a cutoff wall, a subsurface wall constructed into the foundation of a dam. This is some footage from a previous demonstration I built that shows a cutoff wall in action. Notice the length of the seepage flow paths. They're longer, which means the hydraulic gradient is lower. That means less seepage and less chance for erosion. Thank you for watching.
So in that video, it covered dam failures, seepage, the hydraulic gradient, and what happens when seepage becomes too extreme that it causes liquefaction. What it didn't cover in the video that I would like to mention before we continue is that when seepage occurs, it can also cause more seismicity to occur in an area, and there's much research and investigation into the involvement of dam seepage and liquefaction playing a role in seismicity. Now I want to show you all a simple graphic. This simple graphic is a problem with building codes, and I'll play a short simulation after that will provide an additional perspective on unreliability of building codes. Here we have Building A and Building B. Building A has the same building codes as Building B to help reduce damage during seismic events. Building A is the reference building that the building codes were based upon when retrofitting the entire neighborhood. The neighborhood includes both A and B. However, Building B might have the same codes in place, yet the fault beneath Building B causes for surface variations not accounted for in the building codes. Thus, Building B experiences significant damage during the same seismic event that Building A is experiencing. Excuse me. Even though it shares a neighborhood with Building A. Now let's play the simulation. These are the same buildings, same building codes, same building codes, same seismic event, but different underlying properties of the surface. As you can see, the building on the left collapses, whereas the building on the right is able to sustain the small seismic event. With very minimal damage. So now let's go into long-term solutions. Global initiatives have found the success of mitigation techniques against natural hazards and long-term solutions. And the long-term solutions include community training, sustainable ecological cities, and debris management. Community training involves government and community interaction. This lecture is a perfect example of community training, as it involves the BMKG collaborating with the USGS and the USAID in order to bring awareness and understanding to the students, you, and or to the observer, that there is a way to properly mitigate against hazards and natural disasters. And so that way you can take your learning material that you learned today and take it back to your families and friends and your network and help them to better understand initiatives that you have learned during this training. Involvement of government agencies with private and public entities in the development of training programs greatly increases resiliency scores of vulnerable communities and allows for a concise community network to develop on combating against natural hazards and natural disasters. Another long-term solution is green city planning, ecological planning, or sustainable planning. The construction of resilient neighborhoods that consider the environment and city development projects. In this example that we see here, there's a building next to a river. Whereas this river would normally put the building in a high flood zone area, the utilization of aquaculture channels, stabilizers along the foundation, and fortified enhancements along the embankment provide the home with resistance against inundation. There's also the importance of urban distancing that's being shown. Creating tight-knit communities or impacted cities increases risk exponentially, as collapsing infrastructure during a disaster event is able to cause significant damage to adjacent structures. Spacing out buildings in a neighborhood reduces the amount of damage that presents during flooding, tsunami, earthquake, and fire-related disasters. Reduced damage means reduced debris. This takes us into debris management. Debris management can be a difficult concept, as public knowledge can be limited on the role of debris in hazard mitigation. Small debris such as plastic, candy wrappers, to large debris, including destroyed vehicles or fallen tree limbs, can create debris barriers. Debris barriers allow for vulnerability in the future when another disaster event occurs. A quick example. We have a damaged vehicle, glass and wood from a collapsed house, and several fallen tree limbs after a flood. Presence of the debris following the disaster event creates a debris barrier that acts as an artificial dam. Heavy rainfall causes another flood a few weeks later, yet nobody has gone to clean up the debris barrier. The floodwaters cannot flow past the debris dam, and so the floodwaters rise instead. Elevated homes are now exposed to inundation and the floodwaters cannot properly drain, and more debris continues to consolidate near the original debris barrier that was left behind from the prior disaster. This debris dam has caused complications in the example. More homes were suffering from damages from the floodwaters because the floodwaters were unable to recede due to the dam barrier or the debris barrier. This can also prevent emergency responders from performing successful rescue and aid operations. It is important to remove debris following a disaster event or whenever debris barriers develop. Debris removal and management reduces damages and costs associated with post-disaster operations. Here's a visual example of what I just mentioned about debris barriers and damming of rivers. We have on the right an image of a river that has undergone flooding. The red lines represent where the floodway would have been. However, due to the fallen trees, trash, and other debris that is collected at the mouth of the river is blocked from the coastline. This has expanded the flood zone to the black lines seen in the image, exposing the houses near the river to floodwaters. Debris management goes hand in hand with environmental protection. We must maintain healthy environments in order to create disaster resiliency. The Ramsar Convention of Wetlands is an example of disaster resiliency initiatives. As a Ramsar Convention focuses on the importance of wetlands as a natural mitigation tactic against disaster events. Disaster resiliency is the objective of hazard mitigation. Disaster resiliency will not happen overnight. It is something that we need consistent updating and innovative approaches to environmental conditions. It requires focus on the importance of sustainable infrastructure, development and implementation of preventative strategies, the reduction of damage and cost, and on the importance of recovery efforts that improve upon existing mitigation techniques. There's not a single solution to hazard mitigation. Hazard mitigation techniques are specific to the environment and demographic of at-risk communities. Public involvement with government, private, public, and international organizations are crucial to improving resiliency scores. And remember that collaboration and communication is key. This concludes our presentation. Thank you so very much for your attention and your commitment today. I just want to end this presentation by stating that during the COVID-19 global pandemic, I hope that you all maintain your health, maintain your safety, make sure to wear your masks, and make sure to socially distance. Look forward to presenting to you on the next lecture, and stay safe.